This market trend analysis projects that the global essential oils industry will reach a valuation of $15.3 billion by 2027, maintaining a compound annual growth rate of 11.8%. This chart shows that demand is heavily concentrated in citrus-based oils. Orange and lemon extracts dominate the volume due to their potent organoleptic properties and broad industrial application. To supply this specific market, the industry relies on a single primary substrate, citrus fruit peels. Scaling production through peels creates significant logistical friction. Citrus fruits are seasonal, and orchards require complex, expensive irrigation systems and strictly regulated flowering cycles to remain productive. There is also a chemical limitation built into the material itself. Citrus peels contain a high concentration of hydrocarbon terpenes, which are undesirable for high-quality commercial oils. Because of these hydrocarbons, manufacturers must perform a step called deterpenation. This is a mandatory, high-cost process required to upgrade the crude extract into a usable, oxygenated form. The industry's growth is restricted by this reliance on a raw material that demands high agricultural overhead and excessive chemical processing to yield profitable compounds. A biological alternative exists that bypasses the peel bottleneck: the leaves of the kaffir lime, or Citrus hystrix. Kaffir lime leaves offer immediate agricultural benefits. They propagate year-round and generate minimal waste compared to the fruit-bearing cycles of traditional citrus. Chemically, these leaves are natively optimized. They produce a high yield of oxygenated terpenes, the specific compounds that producers are forced to isolate from peels at great expense. This natural chemical profile allows engineers to remove the deterpenation step from the production line entirely. Preparation for extraction is also simplified. The leaves only require low-temperature drying and basic grinding. This creates a streamlined, low-waste system that avoids the complex flowering regulations required for fruit-bearing trees. While switching to leaves solves the chemical inefficiency of peels, it requires a new engineering approach to the extraction process itself. The conventional method for processing these leaves is standard hydrodistillation. This legacy approach is slow. It requires long extraction windows and high energy inputs to sustain the process. When kaffir lime leaves are hydrodistilled, the primary chemical yield is citrinolol. Citrinolol has limited commercial value in high-end markets and is used primarily as a base for insecticides. To enter the pharmaceutical and fragrance sectors, producers need a different molecule, isopuliagol. Converting citrinolol into isopuliagol usually requires a separate production stage and the addition of expensive external catalysts. Hydrodistillation leaves the leaf's most valuable compounds trapped in the matrix, leaving engineers with a low-value output unless they invest in costly secondary reactions. A different approach utilizes pressurized hot water extraction, or PHWE. Instead of simply boiling the material, PHWE manipulates the physical state of the water to optimize the extraction. This phase diagram shows the specific conditions required for the process to succeed. By applying high heat while strictly maintaining pressure, the water is held in a subcritical liquid state. In this environment, the hydrogen bonds between the water molecules rapidly stretch and break. Breaking these bonds changes the solvent's physicochemical properties, causing the dielectric constant to drop significantly. This change increases the solvent's diffusivity. The high diffusivity allows the water to penetrate the leaf's cellular structure more effectively, reducing mass transfer resistance. Operationally, PHWE isolates a larger fraction of aromatic compounds in less time than hydrodistillation, reducing energy consumption. While this state optimizes the physical mass transfer, it also provides the exact conditions needed for a chemical reaction. When processing kaffir lime leaves, PHWE enables a specific chemical discovery. At subcritical temperatures, the pressurized water functions as an active reaction medium. The high dissociation rates of water at these temperatures trigger a structural reconfiguration in the citrinolol molecules. The citrinolol cyclizes in situ, converting directly into the target molecule, isopuliagol. This conversion occurs naturally due to the state of the solvent, removing the need for expensive external catalysts. The resulting oil is dominated by high-value monoterpenic alcohols. PHWE simplifies a complex industrial pipeline into a single stage of combined extraction and catalysis. The physical result is a pure isopulegol-rich essential oil. Quantitative analysis reveals a composition of 52.21% isopulegol and 13.18% isopulegol hydrate. This profile allows producers to supply the pharmaceutical and cosmetic industries, shown here. In pharmaceuticals, isopulegol serves as a potent antiviral agent. It also functions as a direct chemical precursor for menthol. This precursor capability meets the high demand for menthol in the flavor and fragrance sectors. By replacing citrus peels with kaffir lime leaves and adopting PHWE, the industry bypasses the deterpination bottleneck and eliminates external catalysts, establishing a sustainable route to high-value essential oils.